Hello, today we're going to talk about exponential sequences. Alright, this video is just a review over exponential functions and how to graph them and what they are basically. So exponential functions, base formula is written like this. Now the thing we use now writes differently. I like this. Alright, if you want to find your y-intercept here, you just plug in 0 for your x. Whatever you get is what you get. Now, unlike a linear, this has 4 different ways it can look. Right? It's a curved line. This side is called exponential growth. Right? It starts small, and it grows up. This is exponential growth, even though it looks like decay. It's just reflected over the x-axis. This is called exponential decay. This is how it looks in graph forms. Now, people get these confused down here, but all this is the decay reflected across the x-axis. So, some formulas on how this would look would be 2 times 4 raised to the x, or negative 3 raised to the x, or just 3 raised to the x. How if you know it's a growth or decay depends on what your b is. If your b is greater than 1, then it's going to be a growth. If your b is in between 0 and 1, it's going to be a decay. Alright, so don't get to thinking that it's just going to be a fraction, because if your fraction is I forgot the name of it, just lost my head. If you have like 16 over 3, improper fraction. All right, if it's like this is still larger than 1, so it's a growth. So if your b is between 0 and 1, it's a decay. If b is greater than 1, it's a growth. So how I would write my decay would be, f of x equals 1/2 raised to the x, or f of x equals 2/3 raised to the x, something like that. Just a fraction that's in between 0 and 1. Right. Now, this can also be written in a table. So my table over here, so if I have x and y, and we'll do 1, 2, 3, 4, and 5, and let's plug it into the function f of x equals 2 raised to the x. So that would give me, if I put 1 in there, I'd get 2. If I put 2 in there, I get 2 raised to 2, which is 4. 3 in there, I get 2 raised to 3, which is 8. 2 to the 4 is 16, and 2 to the 5th is 32. All right, that would be how it looks when it's a growth. If it's a decay, notice the numbers keep going up, 2, 4, 8, 16, 32, they keep going up. If I do the same thing here, and which one do I have here? I'm just gonna put in the decimals. I believe this is 1/2 raised to the x, if I'm not mistaken, that's what it looks like. It would look something like this, or something like this: 1/2, 1/4, 1/8, 1/16, 1/32. I believe those are the fractions for it. So it can be in decimal or fraction form. You usually want to put it in fraction form because we don't really use decimals anymore. All right, now let's do our next one. So we're going to graph these just to see. That's what we're going to do. We're going to graph 4 more. Here's your first 2. And we're just going to do the numbers 1. I'm actually going to, 1, 2, and 3. All right, so when I plug in 1 here, I get 2. When I plug in 2 here, I get 4. When I plug in 3 here, I get 8. So those are my points, and I want to graph them. Whatever the number is back here is your horizontal asymptote. Since it's 0, it doesn't get into the lesson, so I won't get into it here. So my first number is at 1, 2. My next number is at 2, 4. My last number is at 3, 8. And I graph it. Now I know my y-intercept is going to be 1 because when I plug in, when x equals 0, and I plug it in, I get 2 raised to 0, which is 1. So I know it's going to go through 1 also. And I'll even say it, your horizontal asymptote is this number back here. So this is actually saying plus 0. If I put plus 2 back there, that's my horizontal asymptote then. But since it's not there, it's just going to be 0. So that means what the horizontal asymptote is this function will go forever and ever and never touch 0. That's what an asymptote is. Every exponential function has one. All right, so now let's graph this one over here. I'm going to throw in a negative 2. Make it a little bit more difficult. So negative 1 raised to the 4, so 4 raised to negative 1. When you have a negative, that means that take the reciprocal. So this becomes, I'll write it down here. So 4 raised to negative 1 will equal 1 over 4 raised to the first, which is just 1/4. Raised to 0 is 1, raised to the 1 is 4, raised to the 2 is 16. So this is 4 raised to the 2, this is 4 raised to the 1. This is, sorry, it's 4 raised to 3, which is 64. 4 times 4 times 4. Now I graph it. Ooh, I'm just gonna call this right here 70, call that 60, just to make this easier. And then, ooh, call that 10, call that 20. This is gonna look like a jacked up graph, but that's all right. Negative 1, 1/4 would be around right there. 0, 1 right there. 1, 4 right there. 2, 16 right there. And 3, 64 right there. There we go. That's how you graph it. These are both gross because our base number is a whole number that is greater than 1. All right, now graphing 2 exponential decays. And I know it's a decay because my base is between 0 and 1. So I'm just gonna do 1, 2, and 3. So, well, I'll do negative. I'll do negative 1 over there. Yeah. Yeah, why not? So this gives me 1/2, because 1/2 raised to the 1 is 1/2. 1/2 raised to the 2 is 1/2 times 1/2, which gives me 1/4. And then 1/2 raised to the 3rd is 1/3 times, 1/2 times 1/2 times 1/2, which gives me 1/8. Graph it. 1, 2, 3. Call this 1. 1/2. 1/4. 3/4. All right, now we graph it. So at 1, we're at 1/2. At 2, we're at 1/4. And at 3, we're at 1/8. And I know my horizontal asymptote is good. No, not my horizontal asymptote. My y-intercept will be at 1 because if I plug in 0, 1/2 raised to 0 is 1. So right there. There we go. And that's the graph of that one. Now this one's not hard, it's just a little bit more bothersome, I guess. So x, y, 1, 2, 3. That gives me 1/4, that gives me 1/16, and that gives me 1/64. Now I graph it. I'm just going to graph it kind of the same way I did the other one. It's just going to be a lot smaller. So 1, 1/4, 2, 1/16. There you go. there is your two exponential decay graphs. All right, this has been exponential sequences or exponential functions again. Hope it helps. Good luck.